this video, we will introduce context-free grammar. Till now, we have talked about finite automata, regular expression, Millet machine, Murray machine, conversion of one machine to another machine, etc. and regular grammar. Regular grammar can produce only limited set of languages. There are huge amount of languages which cannot be produced by regular language or regular grammar. So we have superset of that, which is known as a context-free grammar. Language produced by context-free grammar is known as context-free language, CFL. We can represent any regular language using following approaches. One is finite automata, second one is regular expression, and the third one is regular grammar. So if the language is regular, then we can definitely draw finite automata. We can also write regular expression for that, and we can also have regular grammar for that. If language is not regular, then you cannot draw finite automata for that, or you cannot write down regular expression for that, or you cannot write a grammar for that. So all these three forms are convertible. You can always convert finite automata to regular expression, RE to grammar, grammar to finite automata, or vice versa. So it is important to understand what kind of grammars or languages are called regular. And if it is not regular, then how we can use context-free grammar to represent those languages. The simple rule is that if automata requires memory to remember the occurrence of previous symbols, then language is called non-regular. Let us consider the example. Language L1 is equal to a power n b power m, where n and m are greater than or equal to 0. If we note down the strings produced by this language, then that would be epsilon, because n and m both could be 0. So that can generate empty string, that is epsilon. We can have a, b, then double a, b, double b. Then strings of length 3, that would be triple a, double ab, a double b, triple b, and pattern goes on. If we look at this carefully, then occurrence of number of a is totally independent of occurrence of number of b's. The only condition is that number of a's should be followed by some number of b's. That's it. There is no relation between occurrence of a and b. They both are independent. And for this language, we can definitely draw finite automata like this. From state x, we will keep reading a's, and once we are done with a, we can read epsilon. We can move to the y state, which is final state, and from that we can read any number of b's. So this will produce empty string. It can produce a, it can produce b, it can produce double a, b, double b, and all the strings which are present in the language. Consider this example now. L2 is equal to a power n b power n, where n is greater than or equal to 0. So string produced by this language would be epsilon. When n is equal to 1, it would be ab. For n is equal to 2, it would be double a double b, then triple a triple b, 4a 4b, and so on. So if you look at these strings carefully, then number of b's are same as number of a. So for any string, you should know how many a's were there, and that many b's you have to produce. So here there is a relationship between occurrence of a and occurrence of b. That means you need some memory to remember how many a's have been read out in past when you start reading b. Without memory, it's not possible. When you go and read first b, you should know that how many a's have been read out into the past. Then only you can generate the appropriate string. But finite automata doesn't have any memory, and that is why we cannot draw finite automata for this language. You might think that this finite automata can generate this language. Definitely it can generate, but it will also generate the strings which are not in L2. If you look at these strings in L1 and L2, then L2, all the strings of L2 are in L1, but L1 is having some more strings. So L2 is not regular because you cannot draw finite automata for that. In fact, this L2 is super subset of L1, and it requires memory, and that is why it is not regular. So simple concept, wherever we need memory to remember the symbols, it's not regular language. Okay, let us consider a few more examples of regular and non-regular languages. A power n, b power n, definitely it is not regular, as number of b depends on number of a. L2 is equal to WW, where W is a sum string over alphabet A and B. This is also not regular because whatever strings we have in W, same we have to read it again. So we need memory to remember what has been read in past, and same string we have to read it again. So this is not regular language. W power R, where W power R is the reverse string, and W is any string over alphabet A comma B. So if my W is ABB, then W power R would be BBA. So when you are reading BBA, you should have knowledge that I have already read out ABB. That means you need memory to store the first half of the string. So such language are not regular. L4 is equal to A power P, where P is prime number. So again, you need to remember how many exact A it has to read. Next is A power N square, where N is greater than 0. It is not regular. L6 is equal to A power N, B power M, C power M, D power N is not regular because number of C depends on number of B, and similarly occurrence of number of D's depends on number of A. So memory is required and this is not regular. So let us define what is grammar. So grammar is defined by 4 tuples VTPS, where V represents set of non-terminals which are normally capital letters. T is set of terminals which is normally small letters or the digits. P is set of productions. So productions are the rules for generating the strings, and they are able to generate a string by pumping the rules. So we can recursively apply the rules and we can generate the strings. And capital S is initial production. And the grammar is typically represented in this way. P is a set of productions. So we can have productions in this form. On left hand side, we will have one non-terminal. On right hand side, it could be any combination of terminal and non-terminal, or it could be only terminal as well. So S gives AA or S gives BB, then A gives A and B gives B. So this grammar is having 4 productions. It is having 3 non-terminals, that is capital S, capital A, capital B. It is having 2 terminals, small a and small b, and the starting production would be S because there are 4 productions. So from where to start? So we always have to make sure that which production we have to start with. So that is represented by capital S. What is context-free grammar? So context-free grammar is also known as a type 2 grammar. There are 4 types of grammar we will discuss at the end of this unit: type 0, type 1, type 2 and type 3. So the context-free grammar is also known as a type 2 grammar, and type 2 grammar has productions of the following form. So all grammars have specific format of the production. All the rules in type 2 or context-free grammar looks like this. Alpha gives beta, where alpha belongs to capital V. That means alpha must be some non-terminal and the length of alpha should be exactly 1. So on left hand side, we can have only one non-terminal in the production. And beta belongs to V union T whole star. So V is set of non-terminals, T is set of terminals. So beta can take any combination of terminal and non-terminal, even it can take the epsilon value. So on right hand side, it can be any string. On left hand side, it must be one non-terminal. So if the productions are in this form, then those grammars are known as context-free grammar. And the language generated by type 2 grammar is called context-free language. Regular language is CFL, but converse is not true because regular language is subset of context-free language. And like we were using finite automata for the regular language, similarly we have push down automata to recognize context-free language. Few examples of context-free grammar are shown here. Capital S gives A capital S, or S gives SA, or S gives A. So 3 productions we have combined using the pipeline. So pipe represents the OR. So instead of writing 3 separate productions for S, we can club them with the pipe. Let us check the equivalence between DFA, regular expression, and equivalent grammar. If our DFA is like this, as shown in this table, then it can only read one symbol, that is A. And regular expression for that is simply A. And equivalent grammar for that would be given by X gives A. So it generates only one string A. If we have a loop like this, then we know that we can read only B. We can read one A and then one B, then 2A and B, 3AB, 4AB, 5AB, infinite A and B. So regular expression for this would be A star B. And equivalent grammar for that would be x gives ax, because grammar should be able to generate a recursively. N number of a it should be able to produce. So using this definition, we can generate 1a, 2a, 3a or infinite a. And finally, all string must terminate with b. So to stop, we have to replace x by b. So then our entire string will be derivated. Here, initial stage is the final state, and we have a self loop of a on the state. So this will read epsilon, it will accept string a, it will accept string with 2a, 3a, 4a and infinite a. So ultimately, the corresponding regular expression for this would be a star, and equivalent grammar for this would be x gives ax. So using that, we can generate any number of a, and to terminate we can have x implies epsilon. Because epsilon is part of language, so we need to add it explicitly. So these two productions can produce a star language. In upcoming videos, we will see that how to convert DFAs into equivalent grammar or regular expression into grammar. Language of grammar. So if we are given some set of production or the grammar, so language defined by that grammar is defined by L of G is equal to all strings W such that W belongs to T star. It means W should contains all the terminal symbols only. Then only it is a valid string. Otherwise it will be in sentential form. If there is a combination of terminals and non-terminal symbol, then it is not called string. Rather it is called sentential form of the string. And if we start from the initial state S or initial production capital S, then using this grammar G, we should be able to derive string W. The derivation is possible in two ways, either using sentential form or using parse tree. So let us discuss both the forms. Consider the grammar S gives AS or BA and A gives BA or B. So here S is having two production. One is you can replace S by AS or you can replace S by BA. And A you can replace by BA or you can replace A by B. So there are actually four productions, but we have represented using the shorthand notation. We have to derive string W is equal to triple A double B using the leftmost derivation from this given grammar. So let us start with the initial symbol S. S is a start symbol. We cannot start with capital A because just like a NFA or DFA, we always start from the Q0, that is the initial state. Similarly, in grammar also we have to always use capital S or some designated production for starting. Any random production we cannot use to start with. In S, we have two production, AS and BA. We can choose either one. If we choose BA, then the first letter of string would be B. But we know that in W we want A as a first letter. So we are starting with AS. So one symbol from W is read out. Now remaining symbols are double A, double B. This is not a string, it is a sentential form because it is a combination of terminal and non-terminal both. To make it string, all symbols must be terminal. So right now capital S is present. We can replace it by two production, either by AS or by BA from the production of S. If I replace capital S by BA, then initial two letters or initial two symbols in string would be AB. But I want double A as mentioned in W. So I will not choose BA, rather I will choose AS. So capital S we are replacing by AS from the production S implies AS. So two letters are produced double A. So remaining string is A double B that we have to generate. Again, S can be replaced by AS or BA. Still we want A as a third symbol. So again we will replace that capital S by AS. So we will have a 3A followed by capital S. So all three A's have been read out. Remaining symbols are BB. Now capital S we will replace by BA because that will give me the next symbol B which I want in W. So now we are using production S gives BA instead of S gives AS. Otherwise there will be 4A which we don't want. Right? So the fourth symbol is also read out and we are left with capital B only, small b only. And A can be replaced by either BA or B. But if I replace it with BA, then there will be 2B and one capital A. And when we replace that capital A by something, there would be string of length at least 6, but we only have a string of length 5, double A, triple A, double B. So this capital A we can directly replace by small b because that production is available. We can definitely replace that A by small b. And you see that now all symbols are terminal. So this is a string and which is same as W. So we can say that this string is derivable from given grammar. And that is why this string will be part of language generated by the grammar. So this W belongs to L of G. Let us derive the same string using parse tree. So parse tree is a graphical representation or the visual representation of this derivation. So let us start with S with AS. Again S we are replacing with AS. Again we are choosing S gives AS. So 3 A's are generated. Now we have to generate B. So we will replace S by BA and this A will replace by B. And then all the symbols we have to read into the in order traversal. So that will be A, B, B, and that is the desired string. Give the grammar for language L is equal to A power N, B power N, where N is greater than or equal to 1, and also derive the string triple A, triple B. If you note down all the strings in L, then if you look at the carefully, N is greater than or equal to 1. It means N should be at least 1. So when we put N is equal to 1, the minimum length string which we can generate would be AB. With N is equal to 2, that would be A power 2, B power 2. So that would be A, B, B. Then for N is equal to 3, that would be triple A, triple B, 4A, 4B, 5A, 5B, etc. Right? So it is number of A's followed by same number of B's. That kind of language we have. And the grammar for that would be S gives A, S, B. So we know that on one side we need A and we need B on another side. So whenever A is generated, B must be generated. So we will write ASB. So if I replace this capital S by ASB, then it will become now double A, S, double B. If I replace that capital S by AB, then that would be triple A, triple B, something like that. So whenever A is generated, equivalent B is generated in opposite direction. Let us see the derivation. So we are starting with S gives ASB. We are using the first production rule. So we have double A, S, double B. Now we will not replace capital S by ASB because we want string of length 6 only. So that S will be replaced by second rule, that is AB. So now string would be triple A, triple B. And this part is called sentential form because it involves combination of terminal and non-terminal. Right? And the last one is the actual string. And using the and the derivation using parse tree can be shown in this way. ASB, again S is replaced by ASB and then S we are replacing by AB, and then we will read out it in order traversal. Derivation using parse tree for the grammar S gives AB or BA. Similarly, we have 3 production for A, 3 production for B. And we have to derive the rightmost derivation for triple A, triple B string and leftmost derivation for double AB, A double B. So let us see. We are starting with S gives AB because S is by default initial production. So we'll always start with S. Now we have to be careful that which production should we select because there are 2. But we know that our string is starting with A, so there is no meaning of selecting S gives B a production initially, right? So we start with AB, then B is having 3 possibilities, either small b or BS or ABB. So if I replace B by small b, then my string will be over. It will terminate, derivation will terminate and my string would be AB only. If I replace that capital B by BS, then my string would be AB and something. But I want 3A at the beginning, so I will reject that choice as well. And next I will replace the capital B by ABB so that I can have a 2A at least at the beginning. Now there are 2 B's. So which B should be expanded first? So now it is important. Right now we are dealing with rightmost derivation. So the rightmost non-terminal should be expanded first. So at the end of the string, I want small b. So the last b I will replace by b. Now we have to expand the previous b. So still we want 1a to complete the proper string. So I'll replace that b by ABB. Again we have a 2b. So rightmost b we will derive first and then leftmost. And then we'll read out the string and that will be triple A, triple B. For leftmost derivation, again we'll start with the same. Next is also same, but now instead of deriving or instead of replacing the rightmost B, we will consider the leftmost B. So this B will be expanded first because we have to derive the string double AB, A double B using leftmost derivation. So to make it double AB, we are replacing this capital B by small b. Then this capital B, again we are replacing it by A double B. Again we have a two non-terminal symbols. As it is a leftmost derivation, select the leftmost non-terminal first. So this capital B we will replace by B because we want small b. And this also we will replace by B. Let us do that using sentential form now. Leftmost derivation of triple A triple B can be shown as follow. That we are starting with S gives AB and LM stands for leftmost derivation. So whenever there are two non-terminals, we will choose the leftmost first. So let us replace the capital B by B gives ABB. So now we have 2B, and as it is a leftmost derivation, I will choose the left capital B first. So that I have color coded in red. So now we are replacing it again by ABB. There are 3 B's, so we will choose the leftmost one, which is shown in red color. That we are replacing by B. Still there are 2B, choose the left one first and replace it by small b. And finally we are replacing the last one as also using B. So this is the leftmost derivation of given string. Using rightmost derivation, we have to derive double AB, A double B. Again we are starting with the start symbol and RM stands for rightmost derivation. We'll replace that capital B by A double B. There are two symbols, we have to choose the rightmost one. So now you can see the difference in derivation in both. So rightmost B is replaced by ABB. We have 3B, we have to choose the rightmost one, replace it by small b. Then the second last B, that is also replaced by B. And the remaining capital B we are replacing by B. So now we have a string double AB, A double B. The question might be asked in this way as well, that check the validity of the string, whether given string is member of language or not for given production. So we have to check whether 4AB belongs to language generated by this grammar or not. So we should always start with capital S. S gives XY. X is having two choice, double Y or the A. So we will replace it by A because I know that the first symbol we want is small a. Then Y, if I replace by B, then string will be over AB. It is invalid. So I will try to replace it by some other production and I will see if I can generate 4AB or not. So Y I am replacing by capital X, capital Y instead of small b. Again X I will replace by A. Then Y I will again replace by capital X, capital Y. X will replace by A. Y will replace by capital X, capital Y. Again it is replaced by X, A. And finally Y we are replacing by B because I want 4AB. So this string is generated by given production. So we can say that 4AB belongs to language generated by this grammar G. Thank you. That's it for today folks. See you in next video. If you think this video was useful to you, then please like, comment and share. Don't forget to subscribe the channel CodeCrucks. Press the bell icon for the notification of latest videos. Stay connected, stay tuned. Thanks for watching. Bye-bye.